Hello everyone. In this session, we'll discuss matrix operation. So let's see the operations involved. We'll start with the first one as equality of matrix. For this, like we said, we have a matrix of m cross n dimension, and then there are elements within it, aij. So definitely for two matrices to be equal, the first condition is that their size should be same. That is the first condition. Like if the size is not same, you don't have to compare the elements. Same size. And then if the size is same, you'll check for the corresponding elements to be same. So if I say A is equal to B, then let's say the size of A is m cross n and size of B is P cross Q, then m should be equal to P and n should be equal to Q, and then the elements of A, that is Aij, should be equal to Bij for all I and j, right? Then only you'll get the matrices to be same. Like if we have a matrix 2 1 3 4, let's say this is A, then the other matrix, if it is like 3x, sorry, it has to be 2x 3 4, then you can see that if you have to find what is x, you can see if this is first row second column A21, this is B21, sorry, B12, this is B12, it has to be same as this element which is A12. So that means x should be equal to 1, right? Then comes addition of matrices. So the first condition for the addition to be feasible or possible, it is the dimension or the size of both the matrices should be same. So you can say it is possible if the matrices involved in operation are of same dimension, right? This is the first condition. And then what we will do is we'll add the corresponding elements. Right? So if we have, like if we have to do A plus B, we'll have to add Aij and Bij. That is, they'll have to be of the same position, like A12 should be added with B12 and so on, right? For example, if there's a matrix 2 1 3 4 5 6, let's say this is A, and then there is B, which is -1 6 4 3 0 2, then A plus B is feasible. Why? Because this is 2 cross 3 and this is also 2 cross 3, same dimension. And now 2 is A11 should be added with -1, which is B11. So it is 2 minus 1, it is plus of -1, 1 plus 6, 3 plus 4, 4 plus 3, 5 plus 0, and 6 plus 2. So this gives 1 7 7 7 5 and 8. And what is here to notice, the size of A, B, and maybe if this is A plus B equal to C, then the C is also having the same dimension as 2 cross 3. So after addition you'll get the same dimension, right? Now let's see some of the properties. The first one is A plus B is same as B plus A. So it is, you can say, commutative. Then A plus B plus C is same as A plus B plus C. So it is associative. A plus null will give you A. We have already discussed additive, identity. Then A plus minus of A gives 0. This is additive inverse. That is, what is minus A? When you multiply a matrix with -1, it will give you minus A. So A plus of minus A will give you simply 0. Similar operations are involved in subtraction also. We'll talk about subtraction here itself. So if it is A minus B, what does it mean? This is A plus minus of B. Somewhere it is simply a addition operation. So obviously the condition of A and B of same dimension still exists. It has to be of same dimension again, right? So let's say you can take the same example, or otherwise let's say if this is 2 minus 1 0 3 minus 1 minus 2 3 6. So if this is A minus B, this is of 2 cross 2 and this is also 2 cross 2, and of course the subtraction will also give the result to be of the same dimension. So corresponding elements has to be operated. 2 minus 1, minus 1 and minus 2. So minus 1 minus minus 2, 0 minus 3, and 3 minus 6. So this is 2 minus 1 1, and then again 1, then minus 3, and then minus 3. So this is, let's say this is C of the same dimension again, right? Of course, like simple subtraction, matrix subtraction is also not commutative. So I'll say subtraction is neither commutative nor associative, of course, right? Let's move to the third operation, which is scalar multiplication. Let's say it is small c times of capital A. Capital A means the matrix. So scalar multiplication is a multiplication of the matrix with some scalar value C, real value, or maybe imaginary is also fine. So this is C, right? In that case, the operation needs that every element of this A should be multiplied with this constant C, right? So this can be given as C times of Aij matrix, right? Every element Aij is multiplied with this constant C, right? I'll write this: every element of A C. So in the manner we can multiply a factor to all the elements. Again, in the similar fashion, we can take out something similar, something common from all the elements. Like if we say A is, let's say A is 0, 2, 4, minus 6. Let's say this, and this scalar is 5. Then 5 times of A will be each element multiplied with this constant. So 5 into 0 will 0, 5 into 2 10, 20 and minus 30. So this is 5A. And then in a similar manner, if you see these all elements have a common factor 10, we can write it to be 10 times of, let's say 0, 1, 2, minus 3, which is nothing but, let's assume it to be B. So let's say it is 10 times of B. So in the manner we can multiply something, we can take out something also, right? It's nothing but multiplying it with the inverse of that value. Now let's see some of the properties. Well, if we multiply, now that the A plus B is associative, if we are multiplying sum of two matrix A plus B with a constant, we'll get C times of A plus C times of B, of course. Also, C plus D times of A is C times of D, C types of A plus D times of A. And also C D times of A gives CD times of A, or CD times of A. Anything is all same. The fourth one is matrix multiplication. Let's say there's a multiplication C equal to A, B. C is also matrix, A and B are also matrix. And let's say A has a dimension of m cross n and B has a dimension of, let's say, k cross L, right? These two are of two dimensions, m cross n and k cross L. Now for this matrix multiplication to be defined, let's say for this to be defined, we need that these two elements should be of same dimension, or I'll say same, it should be of same value. So n should be equal to k, right? N should be equal to k, then only this multiplication is feasible. And after that, the dimension of C is going to be this m cross L. So C matrix will be of dimension m cross L. Right? And then this matrix multiplication is like we said C. So Cij is obtained by multiplying the ith row of A with the jth row of B matrix. Like the corresponding element should be multiplied in that manner, right? Corresponding element of ith row of A should be multiplied with corresponding element of jth column of B, right? And then they'll have to be added. We'll see this. Let's say we have an example for A equal to 1, 2, 3, 4, 5, 6. So this is 3 cross 2, this is 2 cross 2, and of course you'll see that this number of column of the first matrix and the number of row of the second matrix are same. So if we multiply A, B, we'll get C, and the dimension is going to be 3 cross 2. So this is 3 cross 2, right? How? We'll see that. So this AB is 1, 2, 3, 4. Now we know that C is going to have 3 rows and 2 columns, right? So let's see the first element. This is the first row of A and this is the first column of B. So Aij, like C11, C1 will be first row of A and first column of B multiplied and then correspondingly added. So this is 1 into minus 1 plus 2 into 2. Again for C12, 1 and 2 should be multiplied with 0 and 1. So 1 into 0 plus 2 into 1. Second column, sorry, second row. So second row will move to second row and first column then second column. So 3 into minus 1 plus 4 into 2 and 3 into 0 plus 4 into 1. Third row, so third row and first column, second column. So 5 into minus 1 plus 6 into 2, and then 5 into 0 plus 6 into 1. This will give it to be multiplication and sum. So this is 3, this is 2, in fact these all are same, so this is 4, 6, and then 8 and 5, and 5 and 12, 7. So this is your C matrix, which is of the dimension 3 cross 2 with such and such elements, right? Let's go for the property. First thing is AB is not always equal to BA. It is not associative. In fact, AB, if AB multiplication is possible, BA may not be possible. Like in the previous case, we have AB is 3 cross 2 into 2 cross 2, which is possible because the number of row and number of columns are same. When we reverse the order, if it is BA, this is going to be 2 cross 2 into 3 cross 2. So these two are not same. So this multiplication is not even possible. So forget about being equal, the multiplication may not be feasible also. Next is ABC is equal to AB into C. So if like we are considering that the multiplication is feasible, defined, and then we are considering this property. So this is associative. This one was, I'm sorry, this was commutative. So AB and BA are not always same, which is not commutative, whereas ABC and ABC, that is associative. Also, A plus B into C is AC plus BC. So this is distributive. AB equal to 0 does not imply A equal to 0 or B equal to 0 or even BA equal to 0. If AB is 0, we cannot conclude that A is 0 or B is 0 or BA is 0, right? And if AB is equal to AC implies B equal to C if and only if determinant of A is not equal to 0. This is only possible which is said to be non-singular. So if AB and AC are same, B is equal to C condition, A is non-singular. Non-singular in the sense the determinant value is non-zero. We'll come to that singular part afterwards, right? And next is, like we have seen the diagonal matrix. So for A being a diagonal matrix, let's say A, B, C, and B be a diagonal matrix, let's say D, E, F, then this multiplication of diagonal matrix, like since they are of the same dimension, 3 and 3, 3 cross 3, directly we can multiply the diagonal elements. So this is A into D, B into E, and C into F. Directly, we don't have to do any operation. We can directly write the corresponding diagonal elements being multiplied: A, D, B, E, and C, F. Right? Then and of course it is going to be of the same dimension.